Greetings, fellow space explorers. Welcome to a journey that will take us beyond the stars and into the very fabric of reality. Today, we embark on an exciting journey into the fascinating realm of statistics. This isn't just about numbers and charts. It's about understanding the universe in a way that is both profound and practical. Now, I know what you might be thinking. Statistics? That sounds about as exciting as watching paint dry. But hold on, because what you're about to discover will change your perspective entirely. But trust me on this. Statistics is the secret language of the universe. It's the code that underpins everything from the smallest particles to the largest galaxies. It's the key to unlocking hidden patterns, decoding mysteries, and making sense of the vast ocean of data that surrounds us. Imagine being able to see the invisible threads that connect events and phenomena. In the simplest terms, statistics is the science of collecting, organizing, analyzing, and interpreting data. But it's so much more than that. It's a way of thinking, a method of understanding the world that can be applied to virtually any field. It's like having a powerful telescope that allows us to peer into the heart of complex phenomena and extract meaningful insights. With statistics, we can zoom in on the details and zoom out to see the big picture. Think of it this way. Every scientific discovery, every groundbreaking invention, every technological marvel we see today, all of them have relied on the power of statistics. From the discovery of DNA to the development of artificial intelligence, statistics has been the backbone of innovation. Get ready to be amazed by the elegance and power of this statistical principle. As we dive deeper, you'll see how this simple yet profound concept can reveal the hidden order in the chaos of the universe. So let's embark on this adventure together and unlock the mysteries of the cosmos through the lens of statistics. Now, let's talk about something truly fascinating, the Gaussian distribution, often referred to as the normal distribution. This concept is a cornerstone in the field of statistics and probability theory, and it has far-reaching implications in various scientific disciplines. Imagine you're observing a cluster of stars in a distant galaxy. The vastness of space and the beauty of the cosmos can be overwhelming, but there's an underlying order to it all. You'll notice that most stars tend to cluster around the center, the galactic core, while fewer stars are scattered farther away. This clustering isn't random. It's a manifestation of the Gaussian distribution in the universe. This pattern, my friends, isn't just a cosmic coincidence. It's a fundamental principle that governs many natural phenomena, from the distribution of star clusters to the heights of humans to the errors in scientific measurements. The Gaussian distribution is everywhere, and it helps us make sense of the world around us. It's a fundamental principle that governs many natural phenomena, from the distribution of star clusters to the heights of humans to the errors in scientific measurements. For instance, if you were to measure the heights of a large group of people, you'd find that most people are of average height, with fewer people being very short or very tall. We call this pattern the Gaussian distribution, and it's shaped like a bell, hence the nickname bell curve. The bell curve is symmetrical, with the highest point representing the mean or average value. The curve then tapers off on either side, indicating that extreme values are less common. Why is this bell curve so important? Well, it allows us to make predictions and understand the likelihood of different outcomes. In many cases, knowing that data follows a Gaussian distribution can help us make more informed decisions. Here's the thing. When we collect data in the real world, whether we're measuring the speed of light or the weight of apples, our measurements are always subject to random errors. These errors can be due to various factors, such as the precision of our instruments or natural variations in the objects we're measuring. These errors can arise from various sources, such as limitations in our instruments or slight variations in the things we're measuring. For example, if you're measuring the weight of apples, each apple might have a slightly different weight due to natural differences in size and density. Understanding the Gaussian distribution and its properties is crucial for anyone working with data. It provides a framework for analyzing and interpreting data, and it helps us make sense of the variability and uncertainty that are inherent in any measurement process. So, the next time you encounter a bell curve, remember that it's not just a mathematical abstraction, it's a powerful tool for understanding the world around us. Now let's move on to another fascinating concept in the realm of statistics, the F-test. The F-test is a statistical method used to compare the variances of two populations. It's an essential tool in the analysis of variance, commonly known as ANOVA, and helps us understand the variability within datasets. Imagine you're comparing the brightness of two different clusters of stars. One cluster might have stars that are all similarly bright, while the other cluster might have stars with a wide range of brightness levels. The F-test helps us determine if the variances, the spread of brightness levels, in these two clusters are significantly different. To perform an F-test, we start by calculating the variances of our two datasets. Variance is a measure of how much the data points in a set deviate from the mean or average value. Then we divide the larger variance by the smaller variance to get the F ratio. This ratio tells us how much greater one variance is compared to the other. If the F ratio is close to 1, it suggests that the variances are similar. However, if the F ratio is significantly greater than 1, it indicates that there is a notable difference in the variances of the two populations. We then compare the F ratio to a critical value from the F distribution table, which helps us determine if the observed difference is statistically significant. The F-test is widely used in various scientific disciplines, including biology, engineering, and social sciences. For example, in clinical trials, researchers might use the F-test to compare the variability in response to different treatments. In manufacturing, quality control engineers might use it to compare the consistency of products from different production lines. Understanding the F-test and its applications is crucial for anyone working with data. It provides a robust framework for comparing variances and helps us make more informed decisions based on our analyses. So, the next time you encounter datasets with different variances, consider using the F-test to gain deeper insights into their variability. If you like learning about chemistry for fun, or regardless of why you clicked on this video, subscribe. I will provide a link to the textbook down in the description below. This textbook is the source of all my videos and lectures, and where the information comes from for my analytical chemistry videos. Let's continue back to the lecture. Now let's move on to the t-test, another fundamental statistical test used to compare the means of two groups. The t-test helps determine if there is a significant difference between the groups, making it a crucial tool in hypothesis testing. Imagine you are comparing the heights of two different species of trees. One species might grow taller on average than the other, but how can we know if this difference is statistically significant or just due to random chance? This is where the t-test comes in. There are different types of t-tests, each suited for specific scenarios. The most common ones are the independent t-test, paired t-test, and one-sample t-test. The independent t-test is used when comparing the means of two independent groups, like our two different species of trees. The paired t-test, on the other hand, is used when comparing means from the same group at different times, like measuring the growth of the same trees before and after a particular treatment. Lastly, the one-sample t-test is used to compare the mean of a single group against a known value or theoretical expectation. To perform a t-test, we start by stating our null hypothesis, which assumes that there is no significant difference between the means of the groups. We then calculate the t-value, which measures the difference between the group means relative to the variability of the data. This t-value is compared to a critical value from the t-distribution table, which depends on our chosen significance level and degrees of freedom. If the t-value exceeds the critical value, we reject the null hypothesis, indicating that there is a significant difference between the group means. The t-test is widely used in various fields, including psychology, medicine, and economics. For example, in clinical trials, researchers might use the t-test to compare the effectiveness of a new drug against a placebo. In education, it might be used to compare the test scores of students from different teaching methods. Understanding the t-test and its applications is essential for anyone involved in data analysis, as it provides a robust method for hypothesis testing and decision-making. So the next time you need to compare the means of two groups, consider using the t-test to determine if the observed differences are statistically significant. This powerful tool will help you make more informed conclusions based on your data. All right, we've talked about the Gaussian distribution, the cosmic dance of data around the mean. This elegant curve, often referred to as the bell curve, is a fundamental concept in statistics, representing how data points are distributed around the average value. Now let's delve into a crucial concept that helps us understand how spread out our data is: the standard deviation. This metric is essential for interpreting the variability and consistency of our data sets. Think of it this way. Imagine you have two telescopes, one with a narrow field of view and another with a wide field of view. These telescopes can help us visualize the concept of standard deviation in a more intuitive manner. The telescope with the narrow field of view gives you a very precise look at a small area of the sky, capturing minute details and specific stars. In contrast, the one with the wide field of view shows you a broader but less detailed picture, encompassing a vast expanse of the sky but with less precision. Standard deviation is like the field of view of our statistical telescope. It provides a measure of how much our data points deviate from the mean, giving us insight into the spread and dispersion of our data. It tells us how much our data points are spread out from the mean. When we calculate the standard deviation, we are essentially quantifying the average distance of each data point from the mean. A small standard deviation means our data is tightly clustered around the mean, like a telescope with a narrow field of view. This indicates that the values are close to the average, showing less variability and more consistency. Now here's the key takeaway. A smaller standard deviation indicates greater precision in our data. It means that our measurements are tightly clustered around the mean, and we can be more confident in our results. This confidence allows researchers and analysts to make more reliable predictions and decisions based on the data. On the other hand, a larger standard deviation suggests more variability in our data, which means our measurements are more spread out, and there might be more uncertainty in our findings. This variability can be a sign of underlying factors affecting the data, which may require further investigation to understand the causes. To calculate the standard deviation, we start by finding the mean of our data set. Then, we subtract the mean from each data point and square the result. Next, we find the average of these squared differences. Finally, we take the square root of this average, giving us the standard deviation. This process might seem complex, but it provides a powerful tool for understanding the spread of our data. By breaking down the calculation step by step, we can appreciate how each part contributes to the final measure of variability. Standard deviation is used in various fields to analyze data sets. For example, in meteorology, it helps understand weather patterns by analyzing temperature variations. In scientific research, it helps evaluate the consistency of experimental results. By comparing standard deviations, we can gain insights into the relative consistency and variability of different data sets. A lower standard deviation indicates more reliable data, while a higher standard deviation suggests greater uncertainty and potential outliers. In summary, standard deviation is a vital statistical tool that helps us understand the spread and variability of our data. Whether we're analyzing scientific experiments or weather patterns, it provides valuable insights into the precision and reliability of our measurements. So the next time you encounter a data set, remember to consider the standard deviation. It will give you a clearer picture of how your data is distributed and help you make more informed decisions based on your findings. Now, let's talk about two crucial concepts in science: precision and accuracy. They might sound similar, but trust me, they're as different as a comet is from a black hole. Imagine you're an archer aiming at a target. Precision is like hitting the same spot on the target repeatedly, even if it's not the bullseye. Accuracy, on the other hand, is all about hitting the bullseye, even if your arrows are scattered around it. In scientific measurements, precision refers to how close our repeated measurements are to each other. It's about getting consistent results, even if they're not necessarily on target. Accuracy, however, is about how close our measurements are to the true value, the bullseye of our scientific investigation. Here's the thing: we can have high precision without high accuracy, and vice versa. For example, if our instruments are calibrated incorrectly, we might get very precise measurements that are consistently off the mark. Conversely, we could have accurate measurements that are scattered around the true value due to random errors. The goal of good science is to achieve both high precision and high accuracy. We want our measurements to be both consistent and on target, hitting that cosmic bullseye every time. Like and subscribe. Make sure to share if you found this useful. Be sure to have a nice night, and good night.